Let's start in on limits now. So let's do it this way. We're going to let x be a domain in the real numbers, and we're going to let f be a function from x to r, and we are going to let a be an element of the real numbers. Maybe it's in x, maybe it isn't. And then what do we want? We want to define the limit as x goes to a of f of x. We would like to define a limit, and how do we want and we want it to satisfy the following property. So if we define g of x to equal f of x if x is not equal to a, and then our limit if x is equal to a, and the conclusion is that we would like this function where we've just changed the value at a, or possibly created a new value if a doesn't happen to be in our original domain. Then we'd like this new function to be continuous at our special point A. So let's draw a picture of what's going on here. So let's say we've got a function that looks like this. And then so this function is not continuous at this point A, but then there's one number L such that if we filled in our function, if we set g of a to be L and then just had g agree with f everywhere else, then g is now continuous. And then we'd like to say the limit as x goes to a of f of x is L. So that's what we're going for. So a couple of examples of things that can go wrong. So if we've got, say, this function, then there's sort of no possible value we can fill in. If we set g of a, if we set our limit to be this bottom point, then we aren't continuous, because if you had a decreasing sequence that it converged to a, the values wouldn't converge to L. Conversely, if we tried to fill it in with this top point, then an increasing sequence that converged to a would not the outputs would not converge to L. So this one has no limit. So here's sort of another problem, another strange thing that can happen. So let's say we've got a function like this. So for example, this is f of x is the square root of x squared minus 1. And then and then let's suppose that our point A is here in somewhere far away from the domain. And then when we fill in our g of x here or here, then I could put L here, or I could put L here, or I could put L down here. And the point is, notice that there aren't any sequences that converge to A. Well, technically there's a sequence that's just A, and then the output is going to be L, 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 no matter what happens. And so in the second example, we had the problem that there were no values of L that would work. Here we've got the problem that there are too many values of L that are going to work. So we're going to have to be a little bit careful when we define limit. So let's think about what exactly it means for our g of x to be continuous at A. So we're trying to formulate a precise definition of limit, and notice we're going to want to try to avoid this situation where there are many possible values. So remember, we have our definition in 1.7.1, and that says that G is continuous at A if whenever you have a sequence xn of points in X that also satisfy such that xn converges to A, we have that g of xn converges to g of A, which is L. And then here is a lemma. And this is saying we can simplify definition 1.7.1. So let's have a point in a domain in the real numbers, and since we've already used f and g for things, let's let h be the function from x to r, and then h is continuous at A if whenever you've got a sequence of points contained in X that converges to A, we have f of h of xn converging to h of A. Well, that's just the definition of continuity. So the point of this lemma is that it is enough to look only at sequences that are never the point A, that are never the target point. Let's go ahead and prove this. So one direction is easy. If h is continuous at A, then every sequence in X minus A is a sequence in X So if you've got a sequence in X minus A with which converges to A, then H of xn converges to H of A by definition 1.7.1. And now let's prove the converse, which is the interesting part. So let's suppose that let's go ahead and name this condition, and so I'm going to use the green star as an abbreviation for whenever xn is a sequence in x minus a, which converges to a, we have h of xn converging to h of a. So let's suppose that our condition green star is valid. And let's let xn be a sequence in x, which indeed converges to A. And then a couple of cases. So first case is if xn equals A for all but finitely many values of n, then we've got that f of xn equal h of xn equals h of A for all but finitely many n. So in this case, h of xn is converging to h of A, and that's even by our definition 1.3.1. You don't even need to go on through proposition 1 and 0.3.3a. You don't need the epsilon n definition. You can just work with the interval definition. So now, otherwise, xn is not equal to A for infinitely many n. And then, by our proof of exercise 1.5.1, so there you can draw you can get a subsequence of the xn, and so where xn equals A. So you just, for example, you grab all the n's where xn is not equal to A, and then as we did in the proof of exercise 1.5.1, you just let nk be an increasing sequence, a strictly increased sequence that covers all of them. So we've got our subsequence where xnk is not equal to A for all k. But remember from 1.3.10, we've got our subsequence has to converge to A. So H of X and K converges to H of A. And now we're going to just use our epsilon n definition of convergence. You pick a positive epsilon, you let n be a natural number such that if k is greater than or equal to n, then h of x and k minus h of a, that thing is less than epsilon. And then if n is greater than, let's see, n sub big N, then either n equals nk for some k bigger than or equal to n. So, we've got that h of x and k minus h of a less than epsilon, or we're not in our subsequence, which is the sequence of all the ones that miss a, or x sub n is equal to a, so h of x sub n and minus h of a. That is, in fact, h of a minus h of a is 0 is less than epsilon. So we've got that h of xn is converging to h of a by proposition 1.3.3a. And that indeed completes the proof. So we can now go back here and change our result on from the previous slide to require that our subsequence be an x minus a, not be equal to a at any point. So what we've seen here essentially is that the limit as x goes to a of f of x. That makes sense if there is such a sequence. There is a sequence in x minus a that converges to a. And there's an exercise we did in section 1.6 that we didn't do now, but you're going to do for your homework 21. And in this exercise, we defined something called a limit point. So we're going to define let's suppose you've got a real number and a set of real numbers. Then we say A is a limit point of x if there is at least one sequence of points contained in x minus a So a sequence of points that never actually reaches A, such that xn converges to A. So that is how we are defining limit point. And then so homework 21, the homework associated to this lecture is going to be the following. You're going to prove that A is a limit point of X if and only if for all epsilon greater than 0. Actually, let's go ahead and call that delta, such that there exists a point y that is in X that also satisfies X our y, the distance from y to A. It's less than our delta, but it's also positive, and what positive distance just means is that y is not allowed to equal A. And you will also prove that the closure of X, as defined at the end of section 1.6, that's X union with all the limit points. And that part is not actually all that tricky. That part follows pretty straightforward manner from corollary 1.6.12 and definition 1.6.10. Now we are finally in a position to define limits. I'm doing things in a slightly different order from your book, so we're going to call this definition 2.1.2. So let's let X be a subset of the real numbers. Let's let F be a function whose domain is X. And let's let A be a real number. So then, we're going to need a bunch of cases. So our first case is if A is a limit point. So suppose A is a limit point of X. And let's suppose that there exists a number L, a real number L, such that if you have a sequence in X that's never allowed to be your target point A, and your sequence converges to A, and the definition of limit point is that there's at least one sequence like this, then and the sequence f of xn is also convergent, and the thing it converges to is L. So let's suppose there's a number L where anytime you have a sequence that converges to A, f of that sequence converges to L. Then we say that the limit as x goes to A, f of x is exists and is equal to L. All right. So next case, suppose A is a limit point. Of X, but there is no such L. And this can happen two ways. Either you've got a sequence, either you have a sequence of points in X but not A that converges to A, and such that f of xn is a divergent series, so it does not converge. Or the other possibility is that you've got two sequences. I'm not going to write it down, but we require xn and yn both to be in x minus a. F of xn converges to L. F of yn converges to M. And we've got that L is not the same thing as M. So if either of those things are true, then we say that the limit as x goes to a f of x, we say that does not exist. So limit points are really the points where limits are interesting. That's why we call them limit points instead of something else. But remember, limit points aren't all the points in the universe. There's two other kinds of points. So let's suppose A is in X, but is not a limit point. A is not a limit point. Of X. And in this case, we have a name for that. We call those points isolated points. Of X. And if A is an isolated point, then we say then we don't have any sequences that are converging to A, so we don't have to worry about what happens on those sequences. We might as well just define limit as x goes to A f of x. We might as well just call that f of A. Our function will be continuous no matter what it is. The only special value is f of A. I'd like to say one more thing about this, about the very first case, the case where A is a limit point and L exists. So if A is a limit point, then we want to note some such sequence exists. And then go all the way back to section 1.3. There is only only one L, at most one L, that which with fxn converging to L. So there is at most one possible thing that can be a limit. So your limit cannot exist, but if it does exist, there's only one possibility. You can't have a weird situation where there's two different numbers that both have a solid claim to be a limit. Either there's one limit and only one limit, or there's no limit. Very last option, remember we said that we should, remember you're going to show on your homework that the closure of X is exactly the points that are either in X or limit points of X. So if A is not in the closure of X, that means that none of the above is true. So A is not in X, A is not a limit point of X. So in that case, then there's sort of nothing for your limit to be. There's no natural value for it, so we just say in that case there isn't a limit. And there's precedent for this. Remember that the limit, that if A is a limit point, but there's no target value L, such that we're converging, such that all the f of x n's converge to L, in that case we say the limit doesn't exist either. Let's draw a graph. Let's give ourselves some pictures of all these options. So here's a graph, here is our function. And then let's have some points. A, B, C, D, and E. And then here at point A, we've got that the limit as x goes to A, limit as x goes to A, f of x does not exist, and that's because you can have one sequence of points that's converging to A, where then f of A is converging down to L down here. You've got another sequence of points up here, another sequence of points that's converging to A. F of A is f of xn is converging to M, and then L and M are different. And then limit as x goes to C, f of x also does not exist. And this blob I've drawn here is the topologist sine, is what's called the topologist sine curve. It looks like you can see something like this with the sine of 1 over x, but then you could have, grab these points, the top, the bottom, the top, the bottom. You've got these points are converging to C, but F of these points is bouncing back and forth, so there's no limit. And then over here, limit as x approaches E f of x doesn't exist because there's no point it's in the domain anywhere near E. You haven't got a sequence of points that approaches E. You haven't got E itself in the domain, so there's just nothing for the limit to be. And then the limit of it as x approaches D f of x is just, there is no sequence of points going there. So we're just letting f of D be the limit as x approaches D f of x. And then and then B is really the interesting one. This is the limit as x approaches B. F of x is the, you fill it in with a dot and suddenly it's continuous. And that also works at points like F over here. At a point of continuity, the limit is, of course, the value. And let's state that formally. This is corollary 2.1.3. Let's let A be a point in some domain in the real numbers, and then F be a function from X to the real numbers. And then F is continuous at A if and only if limit as x approaches A, f of x, it has to exist. So it can't be like the point in A or C in the picture above. And also it has to equal f of A. Let's write this out properly, if and only if. And let's prove this. Most of the work we did in our lemma above. That was the lemma where I wanted to work through the little finicky details of sequences in X versus sequences in X that exclude our target point A. F is continuous at A. If and only if, I'm not going to write it out this time, whenever you've got a sequence of points in X minus A with Xn converging to A, we have f of Xn converges to f of A. So then if A is a limit point, of X, then limit as X goes to A, f of Xn, f of X equals f of A. If and only if we label this condition green star, and that's true by definition of limit. And our green star condition, remember, is equivalent to being continuous at A, and conversely, if A is an isolated point, and remember, an isolated point is just a point in X that is not a limit point. Then there are no sequences in X minus A which converge to A. So all none of them. So if there are no sequences, then we say all of them, all none of them satisfy whatever condition you want. So basically all functions are continuous at isolated points. Continuity is talking about, is this function what this function does at this point drastically different from what it does to its neighbors, and if there aren't any neighbors, well, you can't be different from the neighbors. So any function is continuous at an isolated point, but also we have defined limit f of x as x goes to a to be f of a for any isolated point. So our two conditions that we're trying to show are equivalent. They're equivalent at an isolated point because they're all always true. So whether it's an isolated point, which is the boring case, or a limit point, which is the interesting case, we have our two conditions are equivalent, and that completes the proof.